In this chapter, what we'll be talking about are chemical quantities. All right, and so in this case, we're going to be looking at moles, possibly atoms, definitely grams. All right, so we're going to be doing some calculations that are very common in chemical quantities. Okay, so the very first question states, calculate the following. So the first one, first letter, first part A, asks us to calculate the number of lithium atoms. So we're looking at lithium atoms in 4.5 moles. So anytime we're talking about atoms, anytime there's some type of calculation with atoms, we're going to have to use Avogadro's number. And I'll show you that in a few minutes. So start out, we want to start with what we're given. So that's going to be 4.5 moles of lithium atoms. All right. Then we're going to use Avogadro's number. All right. So 1 mole is equivalent to 6.022 times 10 to the 23rd, make that a little bit longer, atoms. And it doesn't matter what atoms they are. It really doesn't matter, because a mole is going to be 6.022 times 10 to the 23rd anything, just as a dozen is 12 of anything. We can have a dozen eggs, we can have a dozen donuts, a dozen cars, a dozen fish, whatever. A dozen is still 12, just like 1 mole is going to be equal to 6.022 times 10 to the 23rd atoms. And this will be moles of lithium. And so the moles are going to cancel, and so we'll simply take 4.5 times Avogadro's number, and what we end up getting is we get 2.71 times 10 to the 24th, and this is going to be lithium atoms. All right, so that's the first one. All these really are is just a conversion, right? We've done conversions before. We've done conversions from the metric system into the English system. In this case, what we're doing is we're if you want to sort of think of it, you can think of it as we're converting it to the atomic system, right? The beautiful thing about Avogadro's number, and we won't get into this a whole lot, is that it allows us to count the atoms by mass as opposed to actually individually counting atoms, right? And it would take forever to count just a fraction of a mole, right? And so instead of measuring or counting them, we can simply use a scale and mass them out. And that's the beautiful thing about Avogadro's number. All right, the second one says we need to calculate the number of carbon dioxide molecules in 0.18 moles of CO2. So B, it's going to be the exact same calculation. We're going to start with 0.018 moles of carbon dioxide. Once again, the identity does not matter. And we're going to use Avogadro's number such that we have 1 mole of CO2 is equivalent to 6.022 times 10 to the 23rd. Oops, I shouldn't have made that. And this is going to be CO2 molecules. All right, so moles of CO2 cancel. We do this calculation, and we get 1.08 times 10 to the 22nd CO2 molecules. All right. Not too bad, pretty easy. But just remember, anytime you're going to be dealing with atoms or molecules, you're going to have to use Avogadro's number. So that's a very good number to know. It's always, I have students ask me, how do you know what to do? Well, one of the keys is here's one of the things you know what always to do. If it's given to you as molecules or atoms and you have to convert, you know you're going to have to use Avogadro's number. That'd be a great time to use that number. All right. C says the moles of copper in 7.8 times 10 to the 21st atoms of copper. So C, oops, we've already used green. Let's try something else. Let's use some blue. All right. So C is, we start with 7.8 times 10 to the 21st copper atoms. We need to convert that into moles, all right? And so in this case, we know that 1 mole of copper is equivalent to 6.022 times 10 to the 23rd atoms, all right? Our atoms cancel, and we're left with moles of copper. And so those moles of copper are going to give us 0.013 moles of copper. I'm always looking down at my notes here in case you're wondering, what are you looking at? I've already done these calculations. You don't need to watch me. But anyway, all right. So in this case, we have the moles of ethane, all right, in 3.75 times 10 to the 23rd molecules of ethane. So we're going to start out with 3.75 times 10 to the 23rd. This is going to be ethane molecules. I'm not going to write molecules up there for space. And we're going to divide this by Avogadro's number, such that we have 1 mole of ethane divided by Avogadro's number. We'll call it atoms. Oops, not atoms. These are molecules. We do this arithmetic and we end up getting 0.623 moles of ethane. Not too bad. Not too bad at all. Pretty easy. Just got a few more problems in this chapter. But that's how you convert between atoms and molecules. Is you're going to have to use Avogadro's number. It becomes a very important number to use. Not that you're necessarily going to do this as a nurse or whatever your chosen profession is going to be, but it's always useful to do conversions. All right, they become quite important. All right, so in this case, the next problem we're going to do is it asks us to calculate the molar mass of each of the following. So we've got to calculate the molar mass. And so the first one is iron, what is that? Oh, okay, iron 2 sulfate. All right, so we got to calculate the molar mass. And the molar mass, what we're going to use the numbers from the periodic table. All right. So the molar mass of iron is going to be 55.85 grams per mole. This number comes from the periodic table. Plus sulfur is going to be 32 grams per mole. Plus we have 4 oxygens. So we're going to take 4 times 16.0 grams per mole, and this will be for oxygen. So once again, I'm just going to write up here in a different color. This is the mass, the molar mass of iron from the periodic table. This is the molar mass of sulfur from the periodic table. And this is going to be the molar mass of 4 oxygens because we happen to have 4 oxygens. And we're going to sum all these numbers up, and what we get is we get 151.85 grams per mole for iron sulfate. All right. Next one, B, is going to be aluminum, and this is aluminum oxide. So we're going to once again sum up the 2 aluminums. The 2 aluminums, each aluminum is going to be 27 grams per mole. I don't know why I looked that up. I should know that. And then the 3 oxygens is going to be 16.0 grams per mole. All right. So we're going to take 2 times 27, basically 54, and then the 48 right here. And that should give us a mass of 102 grams per mole. All right, so that's going to be for B. In lieu of time, I'm simply going to write the next one up here. This happens to be saccharin. So saccharin is C7H5NO3S. So that's going to be saccharin. That's an artificial sugar sweetener or artificial sweetener. And so the molar mass of carbon is 12 grams per mole. However, we have 7 of them plus the 5 hydrogens. 1 point, what did I give that? We'll just call it 1. 1 would be good enough for that. So molar mass of hydrogen is going to be 1 plus 1 nitrogen, which is going to, I have 14.01. I should write grams per mole, sorry. Plus 3 oxygens. Plus a sulfur, which is 32 grams per mole. So if you sum all of these up, what you end up getting, what one gets, is 183.01 grams per mole. All right. So this will be baking powder, and this is going to be NH4, 2 of them, plus CO3. And what this is it's this parentheses. This means that we have 2 of the ammonium ions in there. And so when we're going to calculate the molar mass of this, we have 2 nitrogens. So we have 2 nitrogens, and they're going to be 14.01 grams per mole. All right. We have the parentheses 2 simply means we have 2 of these molecules. So we have 2 nitrogens, and then we're going to have 8 hydrogens. All right. Then we have 1 carbon, which is 12.01 grams per mole, plus now the 3 oxygens. So it becomes 3 times 16 grams per mole. All right. We go through and we calculate this mass, and this mass is going to give us 96.01 grams per mole is going to be the molar mass of this. All right. So pretty easy on these things, not too bad. Wait, I apologize. It should be 3. We have 2 of those. One of those. Yep, sorry, this should be 3. Got a little carried away there. Sorry about that. We have here. Now we got to calculate the mass in grams of each of the following. So once again, this problem states calculate the mass in grams of each of the following. So A, we're going to start out with 1.5 moles of potassium. All right, so we are supposed to calculate this in grams. All right, so we want to know the grams of 1.5 moles of potassium. So in order to do this, we're going to use the molar mass of potassium. And so we're going to start with 1 mole of potassium. All right, and then looking at the periodic table, we're going to put the molar mass of potassium. So this number is going to come from the periodic table. You do this arithmetic, and what we end up getting is 58.65 grams. All right, 58.65 grams simply by multiplying 1.5 times 39.1. All right. The next one, B is going to be 2.5 moles of carbon. All right. So 2.5 moles of carbon, we want to come up with that mass. And so once again, we're going to do the exact same thing we did up here. We're going to multiply by the molar mass, but not of potassium, but that of carbon. And so 1 mole of carbon is equivalent to 12.01 grams of carbon. We do this arithmetic, and we get 30.025 grams of carbon. Now, you don't have to report it to this many significant figures. If you just simply wrote 30.0 grams of carbon, that's close enough. All right. Got to do C. So C is going to be 0.25 moles of potassium. All right. You take that number, multiply by the molar mass. I'm going to erase this so it's out of our way. All right, we're going to multiply by the molar mass of potassium. The molar mass of potassium is going to be 30.97 grams of potassium. This is going to be for 1 mole of potassium. We do this arithmetic where we take 0.25 times 30.97. And for that, we're going to get 7.74 grams of potassium. Last but not least, we will do D. D is going to be 12.5 moles of helium. So 12.5 moles of helium. We're going to multiply by the molar mass of helium. So 1 mole of helium is equivalent to 4 grams of helium. One thing I failed to mention is that all these units down here will cancel. I think that's sort of self-explanatory. So 12.5 times 4 should be 50. So this is going to be 50 grams of helium. All right. That's how we do that problem. So once again, you just take the moles, multiply by the molar mass, Now, if you happen to go from grams and you want to go to moles, you take the grams and you would divide by the molar mass. You would just do the complete opposite of this. So next one is cyclopropane, which is C3H, is that 7? Nope, sorry, 6. 6 is an anesthetic given by inhalation. How many grams are in 0.25 moles of cyclopropane? So we're going to start out with 0.25 moles of C3H6. All right? And we want to know, what do we want to know? How many grams? So if we calculate the molar mass of cyclopentane, that's going to be 3 times 12 grams per mole plus 6 times 1 gram per mole. This is going to be because of the hydrogen. So that's going to be 36 plus 6 is going to be 42 grams per mole. Sometimes for carbon I'll write 12.01. In this case I didn't do that. It's not going to be all that different. And so we have 1 mole of C3H6, and then we're going to put the 42 grams of C3H6 up here. We're going to do this arithmetic real quick, and what we end up getting is we're going to get 10 point, so that should be 10 point, yeah. 10.51 grams is what we'll end up getting for that. All right. Next problem, which will be the last problem I'll do tonight for you folks, because they're all sort of the same. You just seriously, those units really help you out. I can't stress that enough. I see a lot of students who don't write the units, and I think a lot of times they don't write the units because I don't think it's laziness. They just don't know what the units are for. So just really be careful on those units, writing those units down. Read the problem. The problem will tell you exactly sort of what the units are. And I always start these problems with the exact, if you notice, I always start the problems with what the problem states, all right? So in this case, the sedative addemeryl hydrochloride has a formula of C15, all right, so C15, H22, so it'll be H22, Cl chlorine, and then NO2, all right? And if we want to come up with the formula mass for this, this is going to be 15 times 12.01 grams per mole plus 22 times 1 gram per mole plus chlorine is going to be 35.45 grams per mole, plus the nitrogen, which is 14.01 grams per mole, plus 2 times 16 grams per mole. All right. So this is how you would calculate the molar mass of demerol hydrochloride, and that is going to equal, I did that right, so it's 283.4. Now we want to know the mass of 0.0, so how many grams are in 0.025 moles of demerol? So we're going to start out with 0.025 moles of C15H22 Cl and NO2. All right. And now we're going to multiply that by our molar mass, which is 283.46. Sorry, I didn't start that out in the best space on the board here. And so if we take that and we so say 1 mole of demerol, I'm not going to write the whole thing, is equal to 283.46 grams. You'll multiply this number by that number, and what you end up getting is 7.09 grams of C15H22 ClNO2. All right. So if you are to give someone 0.025 moles of demerol, probably not going to ask the prescription of moles. You want to mass that out, it would be equal to 7.09 grams of demerol. All right. If you happen to have any questions on this stuff, feel free to ask me. Either email me through the website or whatever you need to do. I'll be more than willing and I'll welcome whatever questions you have on this. This tends to be a little bit difficult for students, a lot of calculations, but if you need some help, don't be afraid to ask. All right, thank you. Have a good day.